One way in which we've discussed how to graph functions so far is to plot their points, right? We could pick some x coordinates and compute some y coordinates, maybe something like -3, -2, -1, 0, 1, 2, 3. And then based on the equation of our function, we will find those given outputs, right? So if we had a function f of x, this would be f of -3, f of -2, f of -1, and so on. And then we can pair these up as coordinate pairs. So -3 comma f of -3, -2 comma f of -2, and so on. And then we take these points and plot their coordinates on the Cartesian coordinate plane. We use the x values to determine how much we move left or right horizontally, and then we use the y values, or the f of x values, to determine how much we move up or down vertically. Here's our x, here's our y, or our f of x axes. And this is a great way to do it, except in a lot of cases this can take a number of different computations, a number of different points to plot, and ultimately can become pretty tedious. And even more so when we are doing it over and over again for functions that are pretty similar. So if instead we can start to build and develop a collection of sort of standard functions and what their graphs might look like that we'll use pretty frequently, and maybe how to make adjustments to those given a few different parameters, we'll be able to get a sense of what a particular function looks like on a graph a lot faster and a lot more intuitively. And this is where we'll utilize a various set of transformations of functions. Now, this does rely on having a place to start to transform from to begin with, and so that's where we'll start this video today. And so what we'll need to do first is look at a few common parent functions, calling them parent just as in like the standard base level function of which all of the transformations will originate from. So for example, we are already familiar with constant functions, right? These would be functions of the form y is equal to d. Similarly, and sort of an extension of this would be a linear function, which we've been working with in the past few videos. And the base level linear function would just be y is equal to x, right? There's no other additional parameters, no other additional numbers or quantities involved. It's just the output y equal to the input x. And that line is represented on the graph here, running through the point 0, 0 with a slope of 1. We can look at the absolute value function, which, although we haven't discussed much yet in this video series, essentially looks like a V because it's going to represent the line y is equal to x from 0 to infinity, and the line y is equal to -x from -infinity to 0. Right? This is because the absolute value takes any input and gives back the positive version. Right? So for instance, the absolute value of -3 is equal to 3, and we see that here on our graph, but also the absolute value of +3 is equal to +3, which we see here on the graph. And so for whatever input we have, we get the positive version as the output, ultimately resulting in this V-shaped graph. You may be familiar with quadratic functions from an algebra class. Right? These are shaped like a parabola and come from the parent function of y is equal to x squared. Again, no other additional parameters, no other additional numbers, we just have the variable term with the exponent. Similarly, we can also think about cubic functions. These look sort of the same as the x squared, except on the right-hand side of the y-axis, it curves up, but on the left-hand side of the y-axis, it curves down. This is because anytime you square a negative number, it becomes positive, like we see on the quadratic graph, but anytime you cube a negative number, it becomes negative, like we see on the cubic graph. And finally, another function that's going to be important for us to be familiar with is the square root function. This is another you may have seen from an algebra class, but it looks something like this when we're given the equation y is equal to square root of x. Now each of these, y is equal to d, y is equal to x, y is equal to absolute value of x, to x squared, to x cubed, to square root of x, all of these equations represent that kind of base level function, the parent function of all these different cases, where we haven't added any parameters yet that would manipulate the shape or transform the shape of our function. Keeping these in mind and having the collection of all of these images with all of these equations in your memory bank is going to be what's going to allow us to get from a new equation to the final graph based on transformations rather than just plotting points a lot more efficiently. And so what does all this mean anyways? What does it mean to be a transformation of a function? Well, more or less, if we start with an equation like y is equal to x squared, we're going to take that and maybe add something to it or multiply it by something in a certain way that has a particular type of effect on the graph. And the first type of these that we'll explore is called the vertical shift. And so let's imagine that we started with a function f of x. So for function f of x, and let's use a real number which we'll call d. So and real number d. We can say that the graph of y is equal to f of x plus d. So adding that number to our output of our function, y is equal to f of x plus d, is the same as the graph of f of x, except it's shifted vertically by d units. So the same as the graph of f of x shifted vertically by d units. And depending on whether or not d is a positive real number or a negative number, will tell us whether this shifts up or down. And so let's see if we can take a look at how this might work. Let's consider the graph of the absolute value of x. Y is equal to absolute value of x. This is pictured here with the dashed black line on the right, but also below this you can see I have the equation of the absolute value of x plus that quantity d. Now if I click this on, you'll see it just looks exactly the same as what we have, but that's because here d is set to equal to 0. If we change d, however, and we can do so with this slider, if we change the value for d, we'll start to see this graph shift up and down. So for example, if I move d positive, we can see that lifts the graph up by however many units of d, right? So in this case, d is 2, and we can see our graph moves up by 2 points. Or if we make d negative, that shifts the graph downward. Okay, and so depending on the sign of d, this will determine whether our graph shifts up or down and by how many units. And so the graph of y equal to fx plus d is the graph of f of x, but shifted vertically upwards by d units when d is greater than 0, and downwards by d units when d is less than 0. In other words, if we add some value to our function, it's going to shift everything up. If we subtract some value from the function, it's going to shift everything down by whatever that value is. For example, if we imagine that the graph shown here depicts the function f of x, we can graph f of x minus 2 by taking all of the points of this line and shifting them down by 2. In other words, subtracting 2 from their y values. So we can look at a point like 3, 4, subtract our y value by 2, and in this case get 3, 4 minus 2, or 3, 2. We can take a look at our other point, negative 2, negative 1, and do the same. We take f of x and subtract 2 to represent a vertical shift down by 2 units, giving us negative 2, negative 1 minus 2, or in other words, negative 2, negative 3. We can see those reflected on our graph as well if we plot those points. If we look at 3, 2, that's going to live right here. And if we look at negative 2, negative 3, that's going to live right here. And so if we draw a line between these 2 points, we can see that this shift has taken everything from that black dashed line and pulled it down by 2 units. And so this graph here would represent f of x minus 2. Now, if we can shift everything up and down, if we can shift everything vertically, it's probably fair to assume that we can also shift everything left to right. We can also shift horizontally, and that is going to be the case. The horizontal shift will work similarly. So let's once again say for function f of x and real number, this time we'll use c, and real number c, the graph of f of x minus c, right? So this time the c, the real number, is being plugged into the parentheses, so it is part of the input of this function. The graph of f of x minus c is the graph of f of x, but shifted horizontally. So is the graph f of x, the graph of f of x shifted horizontally. And similarly to the vertical shift value of d, when c is positive or negative is going to determine whether or not this shifts us to the right or to the left. And so this will shift horizontally to the right by c units whenever c is positive. So when c is greater than 0. And so it shifts towards the positive axes or towards the right when it is a positive number. Similarly, this will shift to the left towards the negative side of the axes by c units when c is negative, or in other words, when c is less than 0. And if we bring it back to Desmos, we can see this using the graph of the function y is equal to x squared. Right here in the black dashed line, we have just the parent function x squared. Here in the blue line, we have y is equal to x minus c squared, where c is 0. So there is no shift yet. And so if we start to take this value of c and move it to the right, what we'll see is the function also slide to the right from there too. So as we make this positive, our function slides to the right, and as we make c negative, our function slides to the left. Again, similarly to how a positive vertical shift value brought us up towards the positive y-axis, a positive horizontal shift value brings us right towards the positive x-axis. Now, in order to make that work properly, it is important to note here that this is x minus c, right? So our input is x minus c that's going to make this work. But as long as we have that and keep that in mind, then a positive c value, so like x minus 2, brings us 2 units to the right, and a negative c value, like x minus negative 2, or x plus 2, brings us 2 units to the left. And so in other words, in this case on the left, where c is less than 0, specifically c is equal to negative 2, we have x minus negative 2 squared, or in other words, f of x equal to x plus 2 squared. And on the right, we have an instance of c greater than 0, specifically c is equal to positive 2, and so that gives us the function f of x equal to x minus 2 squared, depicted in green here on the graph. And so we can explore in a similar example here how our graph of f of x might be shifted 2 units horizontally. And so to graph the function f of x minus 2, right, f of the quantity x minus 2, we're going to be shifting all of our units to the right, which means we're going to be changing all of our x coordinates by 2 units. So if we take a look at our points here, we have the point 3, 4, which when we shift over by 2, in other words, we transform this by f of x minus 2, we're going to be adding that c value, right, plus c here, c is equal to 2. We're going to be adding that c value to our x coordinate. And so we have 3 plus 2, 4, equal to 5, 4. And we can plot that on our graph here. Likewise, the point negative 2, negative 1, when we transform in the same way, we'll add 2 to its x coordinate as well. -2 plus 2, comma, -1. Or in other words, -2 plus 2, which is 0, comma, -1. And so we can plot that point here. And just like last time, drawing a line between those 2 points will give us our transformed function, f of x minus 2. And we can see this because it's taken all of those points along the black dashed line and shifted them over to the right by 2 units. These tools give us a powerful way to manipulate and morph the graphs of functions that we're really familiar with already. But this is just the start. There are a few more of these transformations which we'll look to explore in the next video. But in the meantime, I hope you found these ones helpful and interesting. If you do have any questions, as always, please let me know. I'm happy to help. Otherwise, I hope you have a great rest of your day, and I'll see you in the next one where we can explore this a little bit further.